Hello everyone. My name is Kangya Chen, and I'm now in KA Professor Shaoli Jing's group at Peking University in China. In this work, we investigated the prospects of electromagnetic follow-up observations for binary neutron star mergers with the help of early warnings from Decihertz GW detectors. The first BNS merger, GW170817, was initially alerted by the advanced LIGO and Virgo detectors, and the GW signal was followed by intensive observations across the whole EM spectrum. Because of this, it marks a spectacular success of multi-messenger astrophysics and has been viewed as the watershed moment in astronomy and physics. However, the fast-evolving nature of short gamma-ray bursts and kilonova E might appear discouraging for multi-messenger observations, let alone the fitness for current EM follow-up facilities due to their off-axis geometries and the large distances between most BNS mergers and the Earth. Owing to many difficulties for all-sky multi-messenger detections of BNS mergers using the traditional time-domain survey projects, some studies have been devoted to the best searching strategy with ground-based GW triggers. However, as we can see, due to the higher sensitive frequency range, they cannot offer alerts as early as the Decihertz GW detectors in the future, even for the low latency GW trigger events. Moreover, we will show in this work that the localization and the timing accuracy of BNS mergers by spaceborne Decihertz GW detectors can achieve a level of 0.01 square degrees and 0.1 seconds respectively. We further propose that such results will allow us to prepare a realistic wait-for pattern for the gamma ray satellites and optical survey telescopes with current or future designs. This will bring excellent opportunities for future multi-messenger astronomy. More specifically, we obtained the GW early warnings only from B-DECIGO and DO-Optimal for more comparisons, and use the facial information matrix to obtain the parameter precisions of each merger event. The SNR threshold is set to be 8 in this work, and our attention will focus on the accuracy of angular resolution delta omega and the accuracy of time of merger delta Tc. A key parameter Te represents the early warning time before the BNS merger, corresponding to the integration upper limit in the frequency domain for the Fisher matrix. We mainly present the results with Te equaling to 1 day in this work. For the redshift distributions of BNS mergers, we have considered 4 kinds of population models shown in this figure. Note that we only use the samples whose merger time since the mission begins will be in this range. This is because we set a 4-year mission time for the 2 Decihertz GW detectors in this work, and our previous study has analyzed and concluded that this population not only makes up the majority of the total BNS mergers, but also yields the best and the most stable estimation results. Based on the GW early warning populations, we can now explore the multi-band EM follow-up detections. We first briefly introduce the sGRB observations. Among a variety of jet energy profiles, we adopt the Gaussian structured jet model. With these above assumptions, we can obtain the gamma band flux for each BNS merger. All related parameters are fixed to their median values for simplification from the Ryan's recent work. We not only adopt the same setting of 4 gamma ray detectors as in Yu et al.'s work, but also consider the hypothetically optimized devices. We artificially set their sensitivities to be 1 and 2 orders of magnitude better than the current designs. For all sGRBs, their spectrums are all described by the band function, and thus we can compare their fluxes and the effective sensitivity limits of different gamma ray detectors in the same energy band. For the kilonova detection, Lee and Paczynski have first predicted these transients with a duration of a day to a week after BNS mergers. We follow Zhu et al.'s work to adopt the model generated by the POSIS package from the multi-band kilonova data. It mainly considers a polar-dominated length-night free component and an equatorial-dominated length-night rich component with different opacities. However, on the other hand, the presence of bright jet afterglows may affect the kilonova detections for on-axis or near-axis observations. In view of this, we further define a detectable kilonova event with the two criteria. TKNP is the peak time of the kilonova, and the F nu star is the effective limiting flux for different optical survey telescopes, which can be calculated with the known such limiting magnitudes. Furthermore, we classify the kilonova detections into two groups based on the observations of sGRB and kilonova. Note that three proposed survey projects with three most common filters have been considered in this work. And again, we have considered a HOD for CSST with 1 magnitude better sensitivity than CSST in each band. From this table, we can see that the FOV for each project can cover about 1 square degrees of sky. For the detailed results, we first present the yearly sGRB and kilonova detection rates. In this table, we summarized all our simulated joint GW-sGRB detections by different gamma emissions for B-DECIGO and DO-Optimal. These results are for different BNS merger populations with an early warning time, TE equaling to 1 day. In each cell, we list the result with the current design for each gamma ray detector as the first entry and present results for HOD1 and HOD2 as the second and the third entries, which are separated by 2 slashes. Using the log normal population model with TE equaling to 1 day as an example, we also list the joint GW kilonova detection numbers and percentages in this table. 3 values in each cell represent the results with G, R, and I filters. For the characteristics of these multi-messenger events, we also take the LN model with TE equaling to 1 day as an example. We first compare the delta omega to delta TC and the redshift to viewing angle distributions of our yearly early warning samples for B-DECIGO and DO-Optimal. Based on whether they can be observed by different gamma ray detectors, we mark these events with circles in different colors. We can see that the sub-square degree localization uncertainty can be achieved, which will be totally covered by different gamma ray detectors and optical survey missions as well. For the multiband kilonova detections, we also illustrate in this figure that the relationship between the peak AB apparent magnitude and the redshift of yearly events. Top, middle, and bottom panels correspond to the detections in G, R, and I bands, respectively. From this figure, we know that B-DECIGO can only detect early warning sources up to the redshift equaling to 0.45. So the majority of its events are expected to have a joint kilonova detections, at least for the CSST. However, it seems rather difficult to detect most early warning events of the optimal due to their large redshifts. Because of time constraints, I have to omit more detailed descriptions and analysis, but all of them can be found in our paper. In conclusion, based on the GW early warning populations of BNS mergers using 2 spaceborne Decihertz detectors, we propose a feasible wait-for pattern as a novel detecting mode for the near future. We point out that one can prepare well in advance for the EM transitions after the BNS mergers and will no longer need to consider the FOV discounts and complex searching strategies like in previous studies. More importantly, such a method provides another opportunity for analyzing the early evolution of each detectable system, such as the properties of pre- and post-merger precursors, and we leave this to a future study. Well, that's all. Thank you.